Imagine you have a list of 10 numbers and another list of 10 million numbers. If I ask your computer to find a number, will both the programs take the same amount of time? And why some apps feels instant while others become painfully slow as the data grows? The answer lies in something that every programmer must be aware of: time and space complexity. See, complexity isn't about how fast your laptop is. It's about how your algorithm behaves when the input data becomes larger and larger. Let's consider the example of a linear search. Okay, the element is not present in the array and the array size is 10. So you will search the 10 elements, and after searching all of them, it will just return -1 saying that the element is not found. What if it becomes 1000? So again it need to search all the 1000 elements and return -1, the element not found. What about 10,000? What about a million? So as the data increases, the search time also increases. This is the complexity of the algorithm linear search. Okay, now you guys might be asking, what is that big O of n? Generally we use three notations: big O, big omega and big theta. There is also little o and little omega and little theta, but we're just going to look about the big ones. So we have best case, that is omega, worst case, which is big O, and the average case is the theta. But we usually consider only big O notations, because if we are capable of working with the worst case ones, that is if the element is not found, that is going to be taking the maximum amount of time. So we are only going to use big O notations. Now let's see about time complexity. Time complexity measures how the running time changes as the input data changes. We are not going to measure exact time, like this test case has taken this milliseconds, this one has taken this much extra time. So we are not going to measure that. We are just going to measure the growth, how it is varying. So let's keep it simple. Let's see this. In the real life, if someone tells, go and take the 10th page, it's very easy for us to open the book and locate the 10th page. What if someone says the topic? Search the topic in that book. So we need to search every single page until the topic arises, or what's the worst case? The topic could not be found in that book. Same thing in the array. If we are going to access with the index, if someone says access the fourth index, access the third index, it's very much easy for us to access it, rather than searching it right from the first index to the last index until the element is found and returning that the element is not found. So how the time varies as the input grows, this is what we call as time complexity, not the exact running time taken by the system. Okay. Now let's see about the three most common and efficient time complexities: O of 1, O of n, and O of log n. See, O of 1 means constant time complexity. No matter how the input might be, how large the input might be, the time taken for that would be constant. As I already said, if you are going to search the 10th page in a book, it's very easy for you, because no matter how many pages the book might contain, you could just simply turn the page and get into 10th position. You don't need to search every single thing. So constant time means no matter how much it is, 2 milliseconds, 3 milliseconds, we don't care about that. If for all the test cases it takes the same time, then it is called as constant time complexity. It will be having a linear graph, so it won't be increasing as the input grows. Second thing is O of log n. O of log n means you are going to divide. Let's take the example of a dictionary. If you want to search some word, what will you do? You go to that alphabet section, and you again eliminate some of the words and go to another part of the section, and you will be doing like that. In programming, what we will be doing in binary search, we will take an array, we will just divide into two, eliminate the one part of the portion and search in the remaining part. Again we'll divide, eliminate and search. This is what we will be doing. So we will be eliminating some part. So this is called log n complexity. Whenever you are dividing, you will be having log n times of complexity. Okay, so it will be having some graph like this. O of n complexity. O of n complexity means that it's just a simple loop traversal. You need to traverse to every single page of the book. Consider this: accessing all the elements of the array using the for loop. So as the input grows, if the input is 10, your loop will be running 10 times. If you are array as 1000, the loop will run 1000 times. So as the input grows, this also grows in a linear manner. So the graph for this would be like this. Now let's see about some less efficient complexities. O of n log n and O of n square. O of n log n. We usually see this in merge sort algorithm where we will just divide them into two and merge them. Dividing takes that log n complexity and merging them takes n. So we get n log n complexity. The graph for this is like this. Now, O of n square. O of n square is considered one of the worst complexities because as the input increases by small amount, the n square just jumps rapidly so high. Say if the n is 10, n square means 100. Now, if n is 20, just an increase by 10, n square becomes 400, which is increased by 300. So, as the input increases by small amount, the complexity becomes way too much high. So we could see this in nested loops and stuff where you do repeated operations again and again, you get this O of n square. The graph would be like this. Now let's just compare all the complexities with this graph. Which one would you prefer for 10 million elements? It's obviously going to be the constant time complexity. You might say that initially it just seems to be a bit higher, right? No, because at initially it's going to be the best case. At the best case, everything is going to take very small amount of time. That is not going to be a problem. We just consider only about the worst case. At the worst case, which is going to be the best? It's O of 1. Next, we just say log n, then n, then we go all those things. The 2 power n comes with a recursive Fibonacci type of problems. When we solve the Fibonacci with the recursion, we just call an is equal to an minus 1 plus an minus 2. So we're just doing this in a recursive manner. It takes exactly 1.6 power n, but we just round it off and say it as 2 power n. So that's it. Time complexity isn't the only thing that matters. Then what about memory? Now let's look into space complexity. Space complexity measures the auxiliary space the algorithm needs, how much extra memory that the algorithm is going to take. This is what we call as a space complexity. It's literally the same like O of 1 means constant, O of n, O of log n, O of n log n. Everything is literally same as we already seen in time complexity. See, constant memory means it's just going to occupy the same memory no matter the input size. But O of n means as the input grows, the space occupied will also be increased. So you could see this example. Now let's see about space-time trade-off. In real world, everything cannot be 100% optimized. Sometimes we trade off space for time, sometimes we trade off time for space. In real world, we could say that database indexing that takes more space. So we traded off the space to get better access times. So we could access it faster. So sometimes we need to trade time for space and space for time. So it depends on the situation on which thing you are working about. So which one, what are the constraints you have? Based on that, you decide which one to trade off. To summarize, O of 1 means excellent time complexity, O of log n is very good and O of n is good. When it comes to O of n log n and n square, it really slows down as the input grows. So don't memorize complexity values, just try to understand how the algorithm grows as the input grows. Once you are familiar with the algorithmic growth, so the complexity growth becomes more and more intuitive rather than just memorizing things. So hopefully it's clear. Thank you for watching.